Hi guys. So what we're going to do today is really revisit some of those applications for exponents that we did earlier this year. Then we're going to introduce a couple new ones and look at just some straight up log applications. Now the reason that we're going to reintroduce these equations that you've already looked at is because now that you know logs, you can solve these algebraically as opposed to just doing what we did earlier with like our graphing and our y count or x count. So we can actually evaluate these a little bit more and show a little bit more of the algebra. Now, like I said, we are going to bring up some new applications. So the first one that you'll notice on there is half-life. Now, you may have already seen this in chemistry, but we're just going to get into that a little bit more, look at that equation, look at how to solve it using logs, and talk about half-life. The other one is the continuous growth equation. Now, this one is very similar to the one we used earlier this year, where we did a 1 plus or minus r to the t. The only problem with the 1 plus or minus r to the t equation is that let's say that was showing like 10% growth. That was showing 10% growth each year, but specifically at the end of the year, it was then 10%. So there wasn't any sort of a compounding factor involved in that. Well, sometimes when we look at growth, in particular, this typically happens most with populations or bacteria or something along those lines. It doesn't make sense for it to be, okay, it's been a year, now let's add our 10% of our people. Okay, it's been this, now we're going to add another 10% of people or another 10% of that population. It's growing over time in little bits and little bits, and you're taking, again, that percent of the people that are there. So you're having that compounding factor kind of take place of it. So that's when this equation comes in. And again, you'll notice it looks the exact same as the continuously compounded interest formula. So really, if their compounding factor comes into play, and for now, guys, I'm going to tell you when to use this equation to get used to it. But specifically, I think the two biggest applications this tends to come in with it would be populations, bacteria growth, something like that. All right, so let's start with half-life. So half-life of a radioactive element is 40 days. It says if you start with 200 grams, after how many days would you be left with 75 grams? So in this half-life equation, A of t is the amount after time. A sub naught is the initial amount. The initial amount is always going to be greater than the amount after time, because if something has a half-life, it's decaying. All right? Then you have T and H. T is time still, time as it has been. H is the actual half-life. So this substance has a half-life of 40 days. That means after 40 days, you'll have half of that substance. After another 40 days, you'll have half of that. After another 40, you'll have half, et cetera, et cetera, et cetera. So T is the amount of time. And again, that unit will be the same as whatever you use for your half-life. So looking at this first one, you start with 200 grams. After how many days would you be left with 75? So this is going to be 75 equals 200, 1/2 to the T, which we don't know, because we don't know how many days. But we do know the half-life. So this is T over 40. So we could just evaluate this with a calculator, but again, we need to get that extra solving practice in. So at this point, we're going to go ahead and solve this algebraically. We're just going to use the calculator at the end to actually evaluate this. So that first step would be to divide by 200. Then we can rewrite this as a log or take the log of both sides, whichever way you're more comfortable with. Then your last step would be to multiply by 40. So 40 log base 1/2 of 75 over 200. At this point, we can go ahead and get a calculator and evaluate this. And I'm going to get 56.6 days. Now, if you think about this, this should make sense, okay? After 40 days, I'd have 100 grams. So I know it needs to be more than 40, right? So after 40 days, there would be 100. After another 40, so 80 total, there'd be 50. So it's not quite, it's going to be somewhere in between those two half-life periods. So somewhere in between 40 and 80, which it is. It's at 56.6 days. All right, so the number of bacteria in a culture is growing at a continuous rate. So we are going to use that E formula. Because again, you're taking that growth in consideration of the ones that are growing as time goes on. The number of bacteria increases from 600 to 1800 in 2 hours. How many bacteria will there be after 4 hours? So what we don't know here is the rate. So we need to solve for the rate before we do anything else. So again, we're going to use that continuous equation. So 1800 is equal to 600 E. We don't know the rate, but we do know it takes 2 hours to get there. Well, let's go ahead and solve this for R. So I would divide by 600. Let's rewrite this as a natural log. Divide by 2. So the natural log of 3 divided by 2, which is going to be about 0.549. Now, I'm not going to use that rounded decimal. I'm going to use exactly this value and exactly that answer in order to answer this next question. So if you round this, you're going to get a slightly different answer. So now it wants to know how many bacteria will there be after 4 hours. So we'll set this equation up again. So I know I'm still starting with 600. I now know it's going to be 4 hours, and now I know my rate. And if you plug that into a calculator, you could just use the answer option to copy that over exactly. Plug that in, and I'm going to end up with 5,400. All right, so next one, going back to our financial stuff. $5,000 in an account, 1.25% interest compounded continuously. So how long would it take to have $5,500? So compounded continuously is our PERT formula. Starting with 5,000, interest is 1.25%. 1.25% as a decimal is 0.0125. I don't know my time though. That's going to be my X. And I want to know when there'll be 5,500. So very similar setup process to what we just did. Divide by 5,000. So that's 55 over 50, which is 11 over 10. Rewrite it as a natural log. Divide by what's with X. And we're going to get our answer. So this would be, at this point, plug it into a calculator. You get about 7.6 years. So this equation shouldn't be new to you guys. But again, now that we know logs, we're actually solving for these algebraically now. All right, so what we're going to look at now are some applications of actual logs, actual log equations. So there's a lot of these that are pretty common. Some of these you may have seen before. One of them is pH in chemistry. So the formula for pH is negative log of the hydrogen ion concentration. So if pH is less than 7, your solution is acidic. If it's greater than 7, then it's basic. So let's say, for example, we've got some apple juice, okay? The hydrogen ion concentration of that apple juice is 0.0003 moles per liter. So I want to find the pH value first. Well, this is actually a pretty easy equation to solve as long as we understand what it's saying. That is going to get replaced with my 0.0003. So at this point, I would just do pH is equal to negative log 0.0003. And at this point, you have to use a calculator. Okay, it's all set up. Your variable's already by itself. Plug it into a calculator, and you're going to get a pH of 3.523. Since that value is less than 7, this apple juice is acidic. All right, another log scale that's pretty common, decibels. Okay, so decibels are used to determine the loudness of sound. If a sound's above 85 decibels, it can cause hearing damage. So it's good to know kind of what your decibels are. So your equation, it's 10 times log I over I naught. Okay, I naught is the intensity of threshold sound. So what we're going to do is use the information given here. It says a cat's purr is about 316 times as intense as threshold sound. So it's not telling us what those values are. It's saying that this is 316 times this. Well, if this is 1, then this is 316. If this is 2, this is 316 times 2. So whatever value I plug in, it doesn't matter. I'm going to end up with 316. So again, another one really easy to solve. At this point, really just got to plug it into a calculator. 10 log of 316 ends up with about 25 decibels. Again, makes sense because it's a pretty small value. Cat's purr is not really loud, probably not going to cause some hearing loss. But again, this log scale really shows you how much that can increase by. Another log scale, there's not an example on here, but I think you have one on your practice problems. The Richter scale for earthquakes is log-based. And what that means is like if something is a 3 on the Richter scale versus a 4, the 4 is actually 10 times greater intensity than the 3 was. You may have also seen some graphs in the news that have log scales. Again, it's just because that log scale, depending on what the base of log is, typically they're using a base 10, it's 10 times more intense for just that step of 1. So you're able to kind of show some different things there. All right, and the last one, this one's my favorite. So experts actually say the most accurate way to convert dog ears to human ears, we don't just multiply by 7 or whatever it is they originally told us. There's actually a formula that's a little bit better to equate it, and that is 16 times the natural log of the dog's age plus 31. So if I want to find the human age of a 15-year-old dog, well, I can do 16 times ln of 15 plus 31. And that's going to be the equivalent human age of a dog. So again, this is another one. You could plug it into a calculator. This dog is going to be about 74 years old in human years. All right, so that's it really for your applications. Again, the log ones are really kind of pretty simple. It's just, I want you guys just to see some of the things that really do use a log scale that are pretty common, and then just getting some extra practice in on solving with some of those applications that we've already done this year.